Okay, thank you very much. Hello, everybody from Madrid. Congratulations for this extraordinary conference. This is the second time that I speak in the ADASS, and both times were online. So hopefully next year we can meet all together. We are almost finishing today, so let me thank you for giving me this opportunity to present our work as invited speaker on how to enable data discovery in big data sets. We will talk mainly about databases, but also other stuff on this category. And so when I saw this category title, this big data, big nightmare, my first thought on the title was about the failure of a database, of a file system, and the nightmare that that would represent. So my name is Pilar de Teodoro, as I was introduced, and I work in the ISAC Science Data Center at ISAC. I'm working as database expert, and within ISAC, I worked as well in the Gaia Science Operations Center. I landed at ISAC from Oracle Iberica, where I was working as consultant. But let's talk less about me and more about the scientific data. So let's start our trip understanding how we end up in the archives, having so much data to handle. The goal of the archives is to enable the data discovery for the different ESA missions to all the astronomers and interested people. You know that this is public data. Here's a quick reminder on how the data arrived to the archives. So we all know that there is a lot of work done before a satellite is launched. But after this is launched, then the data will arrive to the MOC through the antennas to the Mission Operations Center. And from there, it will go to the Science Operations Centers. And among other tasks, they will produce scientific data, they will validate it, or maybe it's validated already it will be validated in the ESDC. So from the SOC, it will go to the ESDC. And here in the ESDC, well, I'm using ESDC or archives similarly. We caretake for 23 missions data for astronomy, planetary, helio, human and robotic exploration missions. So we participate in all phases depending on the archive, so development, operations, post-operations, and legacy. So this will depend on the missions archive, but the main goal is to enable this exploitation and visualization, providing the data and the tools to try to make the life easier to the astronomers. And of course, all has to be done in a cost-effective way, as we need to take care of this data in a long-term basis. So let's see, I hope you have visited already this page sometime, but this is the website for the ESDC. Sorry that the appearance is not very good, but this was difficult to try to fit this into the slide. On the top of the page, you can see some statistics. So we have an average of 25,000 visitors per month, downloading an average of 130 terabytes, which of course it increased dramatically when we have a data release. Currently, the size in the file system where we store our products is more than 1.2 petabytes, although here this is not updated, this is statistics. And I invite you all to visit us in this URL, or maybe this one that looks easier, like the archives.isac.isa.in. So let's review our system stack then at the ESDC. So we were talking that from the SOC, the data will be put in a stage area, for example, and then we will need to ingest it into the archives. And then there are two ways of ingesting this data. This can be if the data are catalogs or something queryable, like for example, telemetry data, it can go directly out to our databases. And if the data is that we want to store is products, then we will use a petascale data storage, as can be, for example, NetApp or the Epsilon. Then we use virtual observatory protocols. So the data can be retrieved then via web portal, for example, with Jupyter Notebooks using AstroPy, for example, or using a science exploitation platform like the data labs that Vicente Navarro explained this morning. So I have here made a spoiler of what I'm going to explain later, but because our databases, well, we will review later what are the main databases that we use at the ESDC. But the thing is that if we go into the direction of storing more and more data, we will need a multi-parallel processing database. Sorry. Okay, now. So this is not the latest movie of Halloween, but having so much data can be killing, and we try to survive. You can understand that data storage is growing for us at the ESDC, and it's very different how it's stored than for the different missions. Okay, this is the size at September 22. And you can see that there are many missions archive data that are really small, kept in the database. That will be, as you can imagine, metadata. And then it starts growing for a planetary, the planetary archive, for LISA Pathfinder, where we keep the telemetry data, for Euclid, that is not in operations because it's going to be launched next year, as you know, but we're already working with a lot of simulations, and of course, Gaia. So Gaia is really a big differentiator here. So we have now like about 42 terabytes of data. So in two databases, one with 37 terabytes for the catalogs and the other one for the auxiliary products. But this will grow a lot because, you know, for this is we have ingested DR3 last June, and in DR4 expected by the end of 2025, this is estimated to be about 400 terabytes. So our model, our solution now has to change from what we have currently. But as I explained, so we have very few data in databases and then big in the for some archives, but then it happens the contrary when we talk about the file repository size. So in this case, the Gaia archive will be very small, and then for other missions archive data, it will be here. The products are stored into the file system. Like we can see that the biggest one is about 200 terabytes of data for Ulysses. As I said, this is all of this makes a total now of 1.2 petabytes, but we really, this is going to be really changing with also with Plato data and with for example, with Euclid data, which is expected to be only for L1 products, 80 terabytes per year. So let's look at some statistics for the Gaia archive, because I think these plots are very interesting to notice, because what we want at the end is to make the systems as stable as possible, even if we have a large amount of data. So we need to take care of this in different ways, right? So we can notice in this plot that this is the data downloaded per month, okay, in the Gaia archive, that people are eager to get the data as soon as it's being released. So it's very clear that we have here 4 peaks, so they correspond to the Gaia releases that has been done. DR1 in September 16, in April 18, DR2, early DR3 in December 2020, and last 13th of June, it was done the DR3. So of course, the amount of the data to be downloaded has increased significantly, and typically this data, if you are wondering if this is downloaded directly from the database or how, we used content data networks, so which are server located in different parts of the world, from where the data can be downloaded by proximity, so to avoid the network latency, of course. But now about the users. So we saw this trend on the data downloading, but also we can see this trend as well of increasing for every release. We can see again the peaks for the different releases, although there are also some other peaks. So we can extrapolate here what can be DR4, and that will be, well, we have to be prepared for that. Apart from this, we are very interested as well in analyzing what are all these peaks, okay, but because this can give us also information about what the users want, what we can offer them. So there is there is a project for data mining the statistics to understand these behaviors. But I think this can make a very good talk maybe for a future ADASS. So let's see how are our database systems at the ESDC. We are currently mainly using Postgres SQL because it's open source. It was created by the academia, by the team of Michael Strombreaker, and it's the academia which contributed mostly with extensions to be used in astronomy. It counts with a big community, so if we get something fancy, we can share it, or you have any question, they really respond very, very fast. It counts then also with these geometrical queries that are extensions, so that allow us to run count searches, cross matches, distances to objects, etc. And also there are some professional companies making a living of Postgres, but so far we are just using them on our own, so we didn't have to pay for anything related to Postgres. We have a full control over the data with Postgres, and of course it runs in several major operating systems. So it's very good to use this for astronomy purposes. For our future, so we said, okay, we are scaling up as much as possible, but then there is a moment that we cannot scale up anymore, and we will have to scale out. And for that, we have run some benchmarks, and this is also what I'm going to explain later. Finally, we have decided to use Greenplum database, which is a distributed solution for Postgres, which is able to handle hundreds of terabytes. And Greenplum claims that also can work with petabytes of data. Well, we have seen some examples of this with professional Greenplum that are working for banks, for example. We use also other database systems like Oracle for the Euclid data processing system, because the data processing system is based on AstroWise. It was developed by the University of Groningen, and they were using Oracle, so we continue working with this. We have also taken some functionalities of using Elasticsearch for ESDC and the Planetary Archive. We have run a prototype of Apache Spark as well for Euclid. This one I will explain later because it's interesting to view. And as well, MySQL, because as you know, telemetry is stored mainly in MySQL databases. So it was very easy to pass the data from one MySQL to MySQL in the archives and then transfer to a Postgres database with Postgres foreign data wrappers. Okay, but many of you will be thinking possibly that when we talk about big data, we just think on non-relational databases, NoSQL databases, or sometimes what is called now new SQL databases. But for us, relational databases works very well even if scaling out, because now things have changed a lot. It was not thought many years ago that this will be possible, but it is possible. And for us, as I said, we depend very much on these geometrical queries. So we saw that we all know that they are great for structured data. We use SQL. ADQL is built on top of SQL. So they are great for complex queries when we have a normalized model, and then we can make these joins to make these queries readable. And also they have and this belongs also to this, to have good relationships and constraints among tables, and this means to have a good data model. And transactionally is very secure because it responds to the ACID, the ASIC principles, and it offers a high reliability. But of course, it has some cons, and we have to admit it. So, for example, it's an upfront. It needs an upfront schema definition, so everything is well packaged. So we will need always a schema to put the data in, and it is not as flexible as the NoSQL will be. Data means that for example, we try to change something, this will affect many other items in the same table or in other tables and so on. And of course, that the processing may be slow. Why? Because maybe we have all seen already data models with 500, 1,000, 2,000 tables in one data model. That will make this system go slow, but although we need then, if we want high performance, we'll have to spend more money. So now let's see some database scaling solutions, because just to avoid having nightmares, the good thing is to be able to understand the scaling mechanisms, and then apart from this, I must say backup, of course, always backup, restore, always to test it. But let's review how can we reach on the scaling to solve the scaling problems that we get into our systems. So I found this diagram on the internet some time ago that I like it very much regarding scaling solutions, and that can be applied to scale from some gigabytes to terabytes and even petabytes. We're still talking about databases here, and the keyword, as I said again, is scalability. So let's review this together. So having here the scheme, well, we need to have clear requirements. So we need to know what are the queries that are going to be done on the application layer. And from then, knowing this, we may be able to build a good data model. Knowing this and what is going to be the purpose of this, then we can know which queries are going to be used, and then which columns are going to be the ones to be used for filtering the data. Those columns are the ones needed to be indexed. Okay, there are different ways of indexing data, but the thing is use indexes. Then later, we know that sometimes there is many queries are repeated and repeated, and we go again to the database to run and run again the same data. But then we should apply what is the cache database queries. This can be done, for example, in a scale-up solution, so putting a lot of memory in it, or putting another server and use Memcache or Redis or other solution, for example. And of course, apart from that, we have the session data. So try to avoid storing the session data, of course, in your database. You cannot start going there and there for checking what are the permissions and everything on the sessions and what was the token inside the database. No, please do it in the client side. And there are also other alternatives then in the case that we have pressure on reading. So there are many connections. So apart from doing connection pooling, of course, then we can have a mainstream system, so a primary database, and then to replicate this data into several standby databases. Then this will allow us that our connections can go, for example, then with a load balancer, it's a proxy, whatever, it can go to use this option of the database read replication. And apart from that, if this is not enough, of course, if our data is growing and growing, what we will need, it will be to distribute our data, to distribute among many nodes. And that is this database sharing. And this is the solutions actually that are being made, not only for SQL databases, but also for non-SQL databases, the database sharing. And of course, then later, well, here there's one word missing, and it's the partitioning. So with the idea of divide and conquer. But then later will be always to scale up and then out, okay? So to accomplish this previous analysis, we need to understand that size matters, and in big data more. Thinking about scalability, when we need to do a good analysis on what will happen when we grow, and that will be about all requirements. So the study will be based on what we want to get. Our queries performance must fulfill the requirements, not only reading, but also on ingestion. We need to prepare a realistic data sample to study the performance of the different systems to measure. And then we will compare ingestion times, retrieving times, administration issues, and problems that can happen. So it's not only about the good performance, but also how much work, how many people we need to have this system as stable as possible. And this is how we will choose over the different systems to be tested. So I'm going to put an example.
10 minutes, Pilar.
Okay, thank you. So I'm going to put an example of the benchmarks we ran to decide as we started in 2018. We knew that the tsunami of data was coming and that we need to be prepared. So we started already in 2018 to make some tests. And these tests were done with the biggest tables that we had available in the archives. Those were for Euclid and Gaia. So at that moment, it was available 3 solutions to distribute Postgres. Again, everything on Postgres because we need extensions for making these geometrical queries. So there were Postgres Excel, Citus by Citus Data, and Greenplum. So let's review a little bit what is this, what they are based about. If you know a little bit on these shared nothing architectures and NoSQL, you will see a lot of similar patterns here. PostgreSQL was a project that started in 2005 as PostgreSQL, and the idea is to distribute the data in several data nodes. Each of them is a Postgres cluster, each of them, and there will be 1 to n coordinators that will allow to connect directly to the database through any of these coordinators. Okay, so I can say coordinator 1 will connect from 1 to 5, coordinator 2 to 6 to 9, etc. Also, the data here is stored in a way that is kept all in one cluster, Postgres cluster that we can query directly. So the data is stored, like, for example, from 1 to 10, from 11 to 20, from 21 to 30, and so on. Everything then has to be, the metadata is in the coordinators, but also there is, for keeping the transaction ready, we use what is called a global transaction manager, and as well there are global transaction manager workers to make this more powerful. We like the solution. It was implemented as well in the coordination unit 7 from Gaia, giving very good results, but we needed with other purposes than them, and we found some bugs. And at that moment, PostgreSQL was supported by a company called Second Quadrant. They ran out of money for supporting the project, so they couldn't continue working on the project. So we said, okay, this is not mature enough because we need a long-term system that will work for several years. We like it very much, the way that it was done, but also the expansion didn't work at that time. I must say that now maybe things are different because this project was taken then continued by the media company Tencent, and they have rebranded it like T-Base project. So CytosDB. CytosDB is an extension of Postgres. So PostgreSQL and Greenplan are forks from Postgres, and CytosDB is an extension. So this goes with the same version, so runs on top of the version of Postgres that will be, for example, the latest one. At that moment, we were running Cytos version 7. That was the beginning of Cytos. The logic is a little bit the same. They changed the name. So instead of coordinators, they are master nodes. Instead of data nodes, they are worker nodes. But we ran some queries, and there were even a single instance Postgres cluster. It was faster than using Cytos. So we just said, okay, we will not use it anymore. Again, things evolve a lot in Postgres and their environments and their surroundings. And now Cytos is in Cytos 11. It was bought last year by Microsoft. It's serving as database as a service in the Azure cloud. And then later Greenplan, which is the one that, well, the spoiler is that you know that is the one chosen at the end. So you can see the difference here with the other solutions is that instead of coordinators, we have master host. There is only one, okay? And then we have a standby master for failover. This is not automatic failover, but it's very important, the interconnect layer, so it has to be very fast. Currently, we are using 40 gigabytes. Then the nodes are called segment hosts, and they have segments inside. This segment, each of them is a Postgres cluster. This Postgres cluster is recommended to have 1 by 2 cores. So for example, we are running now with 80 cores. This means 40 segments, 20 working as primary, 20 as primary and 20 as a mirror. So we get replicated data. So the data from segment 1 and 2, the replication will be in 3 and 4 and so on.
5 minutes.
Okay, thank you. And so the data house store is completely different from the others, because here is not like going in the same like 1 to 10, but 1, 2, 3, 4, 5, 6, 7, 10. So this means we try to parallelize as much as possible. The distributed key is like this, is to try to parallelize as much as possible with Greenplan. So this is the configurations that we were running at that time that we started with virtual machines. Then we were learning some bare metal here at ISAC, then Dell also, because Pivotal started as, it was bought by Dell. And then now is part of Tansu. The community edition is part of Tansu. They keep on developing this. So they have ensured us that this will continue, the community version, because we use this, as I said, for free. So just to put you some examples of where we're running, we have much more information on the benchmark that we run. So if you're interested, you can always email me or talk later. But for example, just a simple query like this, a select count star from a very big table, this flagship mock table, which occupies 1.1 terabytes without indexes on the system and on the database, and with 2.5 billion rows, we can run, well, just to say, the select count star in Postgres is a heavy operation because it's doing a sequential read, okay? So in Postgres Excel, we could run it in 35 minutes. But when we went to Greenplan allows to use different formats to keep the data into the tables. So we use columnar format, a compressed format. Maybe this reminds you to Parquet files, okay? And this we could go down to 14 seconds in this case. So just using bare metal cluster with 5 data nodes, 40 segments using the compression for quick LSET, but we could use it as well with setleaf. I know there's a lot of complexity here with all the acronyms, but just to mention that we went from 35 minutes, the best with Postgres Excel, to 14 seconds with Greenplan. So now some comparison with Apache Spark. In 2020, we ran a proof of concept with Euclid and Gaia catalogs that was very useful, also to compare with Greenplan. The count in this machine was 25 seconds, and we were using Parquet files with snappy compression. The typical use for Spark is also using the analysis of large data sets like table imaging and spectra, the source extraction and pixel data, the spectral analysis, the machine learning. This has been also tested in the Gaia SOC. Running the geometrical queries are based on the SONS algorithm by Jean Gray, using the astronomy extension for Spark that was presented in ADASS 2018, while for Postgres, we use the Q3C quad trees on a sphere. When we compare cross matches in both systems, in Greenplan and Apache Spark, we were surprised because the results were so different. So going deeper in the analysis, we found out that the cross matches were not resolved good on the post. So we notified the XSS developers, and now we hope that will be resolved, as it looks promising as well. So I will go just for some conclusions. Let's go ending this presentation. We need to run into scalable environments. We have more and more data, and we have to be stable in every part of the systems. So as I said, Gaia DR4 will exploit our systems with more than 400 terabytes of data, and Euclid will be like 10 times more, very probable. How great will be also then to be able to cross data between different missions. So maybe we know that Euclid, Plato, and Gaia will go for sure because of their size to Greenplan. Can be different Greenplans or can be only one, because then we can make different parts with dividing by resource. This is one feature of Greenplan that is very interesting. Maybe we can add the rest of archives into this system, and imagine if this could be interesting for the astronomers or not. One thing is clear, time is money. If we want faster retrieval of data, we need to invest on servers, network monitoring, and human resources. Never forget that. This will guarantee that we will not be sleepless, but maybe we can be sleepless about the great science that can be made and with great discoveries. So thank you very much. This is the end of my presentation. This is my email in case that you are interested in knowing more. So that's it for me. Thank you.
Thank you, Pilar, for a great talk. Very interesting.